Hello all and welcome back. So in this video, let us continue our discussion on hash maps, and now we are going to try and implement our own hash map. Okay. So the overall process is quite long and there are many terminologies and operations involved. So we are going to break it down. Just one request, please make sure that you are seeing this full video and make sure that you're completing this in one sitting because that will be helpful in understanding each and everything and how they are connected. Okay. Great. So now let us start, everyone. Till now, we have understood what hash maps are, why are they required, okay, and what are the different ways in which we could have implemented our hash map. We saw how using linked list they can be done. That's the first way. Second was using a BST. Again, we have done each and every operation of BST, so that is something which you can also try on. And the last one was using hash map or hash tables, right? Something which we have to now see that how in O1 approach we are able to do the same thing, right? Great. So let us start now. Let us first think that which is the value which we know which can help us to get anything in a O1 type, right? For example, we have array or list, right? Which we know something in which we can access anything in O1 time. We had this discussion when we were studying about linked list as well. If I know that, let's say this is where my list start, list or array, okay, going to use them interchangeably, and I want to access say fifth element, then I can easily write a of 5, and this is independent of length, right? So it doesn't matter if it's a 10 size, 10 length array, 20,000, 1,000,000. If you say that, hey, you want to access the element at position 5, then I can easily get you that, right? Doesn't depend on length. So this means that it's an O of 1 operation. So that's the very basic idea that we are aware that in a link, in a list or an array, okay, we are able to do this thing via indexing in a O1 time. Now, hash maps are going to be a derived data structure. So we have implemented, like we have talked about how they can be implemented by linked list and BST. For a good O1 complexity, we are going to implement them by using a list. Okay, great. So let us move forward, everyone. Now let us talk in terms of list exactly how this thing can be done, right? Great. So now take an example. Say we have some 5 positions. Okay, so we have these 5 position with us. These are the 5 positions. We have say 0, 1, or let me say it will work, should be fine. 0, 1, 2, 3, and 4. I ask you to store these values such that tomorrow, if I want them, I should be easily be able to access them. Okay, so let's say tomorrow, if I ask you that, hey, I want 3, then you should not have to travel the whole array. Okay, you should be able to store them in this particular array or a list, whatever you want to imagine, in such a way that it gives me O1 overall retrieval. Okay, so how to store for O1 retrieval? For this, pretty sure that all of you will be able to think that it's pretty easy, right? We just have to store each element at index equal to element. I hope that makes a lot of sense, right? Equal to element. So each and every of this element, okay, what can I do? I can store 0 here, 1 here, 2 here, 3 here, 4 here. I can say that these are my indexes. And now you should be able to give me them, right? So if I say tomorrow that, hey, I want 3, you can say that go to index 3, go to, yeah, index 3, and you can get the value there, right? In a way, what we have done is we have applied, so this is known as hash function, right? What we have applied. Okay, when we said that, okay, these are the values, and I want to get corresponding keys for them through which I can store them in my array. They are actually known as, this process is something known as hashing, where we have applied the hash function where n is equals to n, right? So this is some way which we have done. Now let's talk about another example. Okay, so let's say now what we are given is, we have been given an array again. Okay, this time I'm given 0, 1, 2, and let's say 1, 2, 3, 4. But I add one more element, which is 2, 5, 5, 8, 7, 3. Okay, and I make it 6 space as well. So I've done two things. I've added another space, seems fine, and I've added one more element. Now, the logic which we applied in the last overall problem, that would fail here, right? Because ideally, what you can do, you can still say that, hey, I want a very big array or a list where this many elements are there. But I hope you understand this again, then, that it's going to be a lots of memory wastage, right? So a lot of memory wastage if we take a big array or list, right? Yes, we can still say that, hey, give me a 25587 sized array. You can store it in the last. If I ask you tomorrow, you can say that, hey, go to this index. Okay, whatever is the element, that is the index. I can do that. But what about those middle space which is getting wasted, right? Something which we cannot now afford, right? Great. So we are seeing that how it is inefficient, right? It will just lead to lots of memory wastage. Let me write that as well. Inefficient, okay, waste of memory. Great. Now let us take one more example here, everyone, right? In our dictionaries, we saw that how I was able to save each and everything, be it a tuple, be it a string, be it any number, anything. So if I am tomorrow giving you, let's say, keys like this, key 1, key 2, key 3, then what should happen? How are we going to save them? Again, the same problem. Indexing, we saw that it's a constant time operation. That thing was very good. Okay. So we should write it down as well somewhere. I think we have not written. We should write it down. So access via indexing is O1 operation. So we see that how efficient it is, right? It's a constant time operation. All is good. But I hope you understand the problem now. What if we are not able to map the thing which I want to store into indexes? And in dictionary, we saw that how all these items, right? How all this key 1, key 2, and key 3, they are also, we are able to solve as, we are able to store, okay, in a dictionary as keys. So that means one more thing, which is that key can be anything as well, right? Key can be anything. And I believe that our aim should be to somehow change the given key, change the given key into an integer, right? Into an integer. And this is what hashing help you to do. Okay, so this is where we will use hashing. So what exactly hashing is? Let us see that, everyone. Hashing, say that hashing is actually just a function. Okay, so we saw that in the first example as well. There is a hash function, okay, which I'm going to apply. It will be taking in key. Okay, it will be taking in the key and it will be giving me out the integer for that, right? So let's say a very good hash function for this problem, which we did earlier, it can be something like this. So for example, it can just say that, hey, get the last element. And hash function can be anything. Like, it's totally a random function. It's on you. You can take anything. Okay. So I can just say that, hey, give me a hash function I'm applying on this keys. It is just I'm getting the s of -1. So in this way, I will get 1, 2, and 3, and I will store them here. 1 here, 2 here, 3 here. It's a perfectly valid hash function. So I will just repeat what hashing is or hash function is. Hashing is this process of changing anything which you are given into your overall integer. Hash function is the way you do it. So hash function is helping you to do it. You have to make some overall, I would say, logic based on which this will be converted. Right? That's the whole idea. So once you have converted, once you have gotten the index, then we can save that in my array. Right? Great. On that note, there is just one more terminology which I forget. So this array or list which we create, this is something which is known as a bucket array. Right? So this is known as bucket array. So we say that we have buckets here where we can store things. Right? So I will repeat what all we have to do. We will be given some keys. We have to define a hash function. That hash function is going to give me an integer. Once I get an integer, then what I have to do? I have to just make sure that using that integer, I treat that as an index and I'm able to store my elements or the values in the bucket array. That's the basic idea, right? If I'm able to do that, then I will be able to get them tomorrow because this hash function remains the same. Like it is not that while storing you are changing it, while getting you are changing it. No, it will always remain the same it is. Okay, so it doesn't changes. It will always give you the same value. If it gives different value, then you have messed up your hash function. It is dependent on something it should not be. So no matter if I ask you, hey, what is the hash value for 5000? Or let's say for this key one, it should always give the same thing. That's the basic idea, everyone. Okay, great. Now many of you might be thinking that all is right, but what if tomorrow I have something as say key 100 here? Won't we get into the same problem again then? Key 100, I will get, let's say, 100 out of it, not 0. I'm saying that let's get the integer. My bucket array is of just size 4. How I'm going to save it? Or let's say tomorrow we create an hash function where you gave me key 1, key 2, something like this, and I'm generating some number. Right? It has some number, let's say key 1, 2, 3, 4, 5, key 1558. I'm getting the integer. Okay. And they are having the size which is greater than my overall size of the bucket array. So perfectly valid things which can happen, everyone. So let us see a little bit more about this hash function. This hash function, okay, we say have two things to do. So hash function, the first thing it does, it gives me a hash code. What's a hash code? Key converted to integer. So if I give it, let's say key 11345, it will give me 11345 or anything based on the logic. Second thing it does is it compresses that key. Okay. The compression is required because let's say if you have just a 5 size array, okay, 5 capacity array, key compressed to have an index present in bucket array. Okay, so pretty logical thing to do. A very good compression function, something which is used a lot is percentage. Like even I can write it down as well. Modulo operator. Because we know that let's say for percentage n, okay, it values always is from 0 to n minus 1. And for my list or array as well, if it is having size n, then it goes from 0 to n minus 1. So I will be sure that whatever value I'm getting after compression, that will be present in my index, right? So I can just use the modulo operator. That's an awesome compressing uh, mechanism or something which we can compress. Okay, great. So now it seems that we actually have been able to compress. Compression seems fine. Now let us talk more about the hash function or how we will get this hash code, right? See, hash code can actually be anything. Okay, so we can have any hash code, okay, which converts key to integer. Key to integer. Great. So that means that I can have even identity as a hash code. So you are sending me, let's say, 0. I will give you back 0. Okay. So I'm saying that identity is the one, the something which we used in the first overall problem, right? Okay. That is fine as well. It will work, but it will work just for integer. Let's see how we can handle for strings. Okay. So for string, this will work. But what we will do for our strings, like let's say if I'm giving you now ABC. Again, we cannot take identity here, right? So that's the same problem we got in keys. Great. Here, what will happen? We can use the sky values. So we know that internally, each and every string is having some sky values, right? So ABC can have 97, A is 97 plus 98 plus 99. So 97 plus 98 plus 99. Okay, great. There is one problem in this as well. So first I will talk about what is a good hash code, right? What is a good hash code? I believe a good hash code is something which makes sure that overall output is uniformly distributed. Okay. We can have even a hash code that always gives you, let's say, 1, right? It's an identity, not identity. It is just some constant hash code. But that will be a lot bad, right? Anything which I'm sending, you are saying that, hey, store it at 1. How am I using it then? My whole aim of hash code is that I am able to better utilize this particular buckets array, right? The better I will be able to utilize it. So my whole aim is to make sure that uniform distribution is there. Okay, so that is pretty self-explanatory. Uniform distribution is there. Now, in the above, where we were adding the sky code, this those seem to work fine. There are a few problems. Let us talk about them. What happened is that, let's say in the last question, in the last video, we talked about anagrams, right? So ABC and CAB are anagrams, and thus they will have the same hash code again. Okay, so it kind of will give you pretty bad results. One more thing is that many of these words, right? So let's say ABC, AB, they will be very near to each other. Like let's say if tomorrow ABD is there will just be a difference of 1 between the hash value of ABD and ABC. A good hash code is one which actually makes sure that all the values which you finally get, the integers which you are finally getting, that is a lot spread across. Okay, they are not concentrated. Okay, so I can write that as well, not concentrated. Great. So let's say tomorrow something is getting us 10, then the next thing I'm getting 20, then 30. I take the modular, let's say by 11, I'm getting everywhere the same value. That's a problem, right? Sorry, I'm taking the modular, let's say by 10. So I want them, they should be a lot spread out. Okay, great. Now, one more thing which we do is we try to add, okay, them as a power of prime number. So I will tell why exactly that is done. A lot of research has actually been done in this. So I have read a lot about different hash codes and everything. What happened is that prime number have a very good distribution. Prime number have very good distribution, and we try to be little far off from power of 2 or 10. The reason is that they are very common in nature. Okay, so we try to be pretty far off from them. Prime number have good distribution overall. So what we use here is, again, this is just some things which have been researched upon by scientists. Okay, and we then make sure that we are able to see that. So the whole idea is the same, that you will be getting some key from a key, you will be getting some integer via the hash code, right? Hash function. So what happens here is, pay attention everyone. Let's say my 321. Okay, this I can write as 3 into 10 to the power 3 or 10 to the power 2 plus 2 into 10 to the power 1 plus 1 into 10 to the power 0. Now what I do is I take this as a prime number instead. They are just written as powers, right? So tomorrow what can I do is, if I'm getting ABC, I can just say that a, whatever I'm getting the value of a, that into some p cube plus b, that again into some p square, something like this I can do. The idea is that because prime numbers gives good distribution, we will make sure of two things. They will be a lot spread across. So I will get two benefits. First is spread across. Second, they will be actually having very high values. Like it will not that they are concentrated somewhere. Okay. So along with spreading, it is like, for example, in the above one, 90, 90, 90, it is around 270 to, let's say, somewhere in the space of 1000, right? That is where my all the keys will, all the integer values of keys will lie. Okay. Because I know that A is 97, B is 98, C is 99. For all the three letter words, they will be very close to each other. Here I have spread them across. Okay. And very large values I'm getting. Very large values. So which is again not an issue because I'm going to take a modulo, right? Very large values. Great. Now the next question is tomorrow. It might happen that I'm asking you to store. As I said, keys can be anything, right? Provided they are not mutable, like they cannot change. List cannot be a key. Tomorrow, if I let's say ask you to store a node, okay, so we created nodes for our linked list and for our trees. What if you have to store a node? What if a node has to be stored as a key? Then again, see, the idea is that we can get, let's say we are using the overall, what we say, the address or the reference for this particular thing. Okay, so we can store it as key. Maybe you can use even the current time and get some hash code. Okay, but that will be a problem because again, we will not be able to reproduce that. So again, we cannot use that. The idea is that they should be always same and unique. Two keys cannot have the different keys cannot have the same hash code. Your hash code should not change with time. So if I'm asking to insert with the hash code, insert a particular key, tomorrow to get, you will need the same hash code, right? So maybe you can use the address because that's going to be the same for an element. Maybe we can check for some values that, okay, what data is it storing? Okay, let me make a hash code based on that. Okay. So yeah, all that thing can be done to make sure that you are able to overall find your hash code. So that is the basic discussion about hash code, where through which we can convert our key into my integer. So key into, we have the hash code here. We will get this as an integer and then we will just save it into a bucket array, right? So that's the whole idea, everyone. I hope the discussion is clear that how will we be able to do it using using a array or a list, right? Great. Now again, many of you might have one more question or you might be thinking one thing. Let's say tomorrow I ask you that, hey, I have these 10 nodes, okay, 10 nodes, 10 words, 10 numbers, okay, which I want to store in a bucket array of size 5. So let's say I have this bucket array of size 5 and I'm asking you to store say 10 numbers in this. Like I'm asking you to store 10 numbers here. Then what we will do? Okay, let me write numbers nicely. It's a little bit dust here, should be fine. Numbers. Well, the problem here is that yes, there will be some collision. Okay, so let's say you written a very good hash code. Okay, what exactly it is doing is it is giving you say 100025. Okay, and then here second, yeah, we are getting 100075 and we can maybe change it as well. Okay, so they are a lot far off. They are a lot far off. Let's say you just take the hash code as the last digit. Okay, or maybe taking percentage by something. Let's say by 10 you are taking the percentage, the modulo operation. Okay, even if you take it by 5, which is the size, you will get the both of them as 0. Okay, so let us take this percentage 5 only. We will get both of them as 0. Now the problem arises that how exactly are we going to handle this case? This is something which is known as collision. Okay, and for this we have some ways we handle the collision. The problem is that two things. First, if you want to store many elements or more elements than the bucket array size, then of course you will have collision. That's the first thing. Second is, even if that is not the case, let's say even if you are taking a 5 size array and you get the same hash code, and sorry, you get the same hash value after doing the calculating the hash code and compressing them. Okay, then what are the different things which we can do? So that's the basic idea, because that is something which is known as collision. Okay, and that is something which we are going to now see in the next video, everyone. Okay, so I can write above is known as collision handling. And don't worry, I will be teaching, writing the code, helping you visualize everything. Okay, so I'm making sure that each and every one of you just get this fear out that how they're implemented, because I see many students struggling with the overall implementation of hash maps. Okay, so great everyone, we will continue this discussion in the next video now, but I'm pretty sure that you would have got a very good idea that why and how things are happening, the start of the things in a hash map. Okay, great, so let's meet in the next video.